In this lecture, I like to work through some examples involving simple harmonic motion, but let me start with a quick recap of where we left off in the previous lecture, which was the expressions for energy in simple harmonic motion. Namely, we had expression for kinetic energy in simple harmonic motion and one for potential energy in simple harmonic motion. Now, um, if we have a mass on a spring system, we showed that the angular frequency of oscillation, the simple harmonic oscillation, was given by square root of k over m. Now let me take the expression for the potential energy, this equation here, and see if we can uh, what it would equate to for the case of a mass on a spring. So we have a mass there for a mass on a spring. So potential energy of an oscillating mass on a spring using this expression up here is 1/2 of m. Now for omega squared we substitute in square root of k over m, so that's k over m. And as you know, this expression here, a squared cosine squared omega t plus phi naught, is simply the displacement, the position for the simple harmonic oscillator. Well, that's squared, position squared. If you recall, xt is equal to a cosine of omega t plus phi naught. So what I have in the square brackets here is simply position squared. So we substitute that in, so that's position squared or displacement squared with respect to an equilibrium, and we end up with the familiar expression for energy of a mass on a spring, which is 1/2 of k, k being the spring constant, k delta x squared. Now, going back to the kinetic energy expression, what I have in the square bracket here is of course nothing more than velocity velocity squared for the simple harmonic oscillator. Once again, the kinematic equation expressing the velocity direction x for a simple harmonic oscillator is minus a omega sine of omega t plus phi naught. So what I have in the square brackets up there is nothing more than the velocity squared. Now taking a look at the system involving a pendulum. In the pendulum we showed that angular frequency is given by square root of g over L. So once again, let's take the expression for the potential energy from up here and substitute in for omega. For this omega squared we put in g over L. And for our position, now the position in the pendulum is the arc length. Let me switch the color of my pen. It's the arc length. Arc length is the displacement from the equilibrium position, which is in the middle here. So instead of this term, the a squared cosine squared term, we simply put in s squared. That's our position term. But as you very well know, the arc length s is equal to L theta, where L is the radius of the circular path, or in this case the length of the pendulum. But we said that pendulum exhibits simple harmonic oscillation, obeys simple harmonic motion only for small theta. And if you look back at your trig identities, you can see that cosine theta, for small theta, cosine theta can be written as 1 minus theta squared over 2 factorial, which is simply 2. So substituting, first of all, for s squared as L squared theta squared, and then substituting in for theta squared as twice 1 minus cosine theta. You can check the algebra, see if I made a mistake or not. We end up with an expression for U, potential energy for a pendulum, as mg L times 1 minus cosine theta. But what is that L into 1 minus cosine theta? Well, looking back at this drawing at the lower left hand corner. um, uh, the pendulum, if it's at this position here, let's say it's at this, it's a height h above the equilibrium, the equilibrium position, and that height h, if you look back on this side, is actually equal to L minus 1 cosine theta, because this part of the triangle is L times cosine theta, and the whole length of this side is L, therefore the red part is 1 L into 1 minus cosine theta, which is equal to H. So making that substitution, we end up with the potential energy of the pendulum at the extreme position is equal to mgh, or at any position in between is equal to mg times the height, which should come as no surprise, because the potential energy is that due to gravitational force, because if you recall, this was the gravitational force which gave us the restoring force for the pendulum. Just wanted to go through this little exercise to show that these generic expressions that we have can be used in conjunction with whatever system that you have. You need to identify the system, work out the forces involved, and come up with suitable expressions for the angular frequency, and then do the substitution. These are generic expressions. Do the substitutions for omega, etc., to come up with the relevant expression for the potential energy or the kinetic energy in each case. Now, let me talk a little bit about a system involving a spring which is hung vertically. So here we have a spring which is attached to a ceiling. It has a length L, unstretched length L. Now if we were to attach a mass m to it and lower it ever so gently, it will settle down at, let's say, this level here, where the amount that the spring stretches by is delta L. Now Hooke's law says that when mass is in this position, the new position, then the spring force, which is upwards, is given by K delta L, where delta L is the amount of extension that the spring has experienced, and the force downwards on the mass is, of course, that due to force of gravity, which is mg. And since the mass is in equilibrium, then mg must equal K delta L. Actually, I forgot a negative sign there. So mg must equal K delta L, and what we thus have is that delta L, the extension, is equal to mg over K. Okay. Excuse me. Mg is equal, delta L is equal to mg over K. So now if we have our mass in this new equilibrium position, so this red level is our new equilibrium position. Please note that when you had the spring and along the horizontal, the equilibrium position was simply the natural length of the spring. However, in the vertical, when you have a mass attached to the spring, then the equilibrium position is not the equilibrium length of this natural length of the spring, but the stretched length of the spring. So now if we get the mass oscillating about this new equilibrium position, we can write the net forces. The net force on the bob is, let's say, in this position, where it's delta y above the new equilibrium position. According to Hooke's law, that's well, the net force is K, which is the spring constant. The spring has a spring constant K. Delta L minus delta Y is the extension of the spring. The spring force is upwards. This force is positive, and mg, the force is downwards, therefore it's negative. So the net force on the bob is K into delta L minus delta Y. Now substituting in for delta L, putting mg over k for delta L, we end up with k into mg over k minus delta y minus mg. So we end up with the F net force on the bob while it's oscillating is simply given by minus k delta y. And minus k delta y, well, that's Hooke's law for a system where the spring is horizontal with the mass oscillating about an equilibrium position, and this is our delta y, plus or minus delta y um, uh, displacement about the equilibrium position. So if you choose your equilibrium position carefully, that is, if you make the equilibrium position the stretched length of the spring due to the mass m hanging to it, then you don't need to worry about the force due to gravity, this mg. It actually cancels out. So a system involving a vertical spring with a mass hanging to it will oscillate, will exhibit simple harmonic motion as if it were a spring on the horizontal. But the important thing is that you need to figure out this new equilibrium position, which is the length of the spring plus delta L, that delta L being the amount that the spring is stretched due to mass m's presence. So in one of the problems, examples in the assignment, we have a spring with mass m which is being held in place, and then we let in place such that the spring is neither stretched nor compressed. Now we then let go, and the mass dips a distance d below the position where we were holding it. Now you have to realize that when you let go of a mass, the mass goes past its equilibrium position and dips as far below as far below the equilibrium position as it started above the equilibrium position, i.e. The amount that it drops is equal to twice delta L, where delta L is the amplitude of oscillation. So this is delta L plus delta L and minus delta L. So delta L is the amplitude of oscillation of the bob after we release it, and it oscillates about this equilibrium position. Now if you were to lower the mass gently, then it will simply stop at this equilibrium position ml. However, when you let go of the mass, its potential energy gets transformed into kinetic energy. So it has some kinetic energy as it passes through this equilibrium position, and it's that kinetic energy that allows the mass to go past the equilibrium position till the spring potential energy equals, well, till all the kinetic energy that it has gets transformed into spring potential energy, and then it gets pulled back up due to the spring force acting on it, and carries on in a simple harmonic oscillatory manner. So the important thing to realize in this example is that the amount that it drops from where we were holding it is equal to twice the amplitude of oscillation, and that amplitude delta L, since we were holding it at the natural length of the spring, is actually given by, well, the delta L is equal to mg over k. That's the argument we had above, so we can substitute in for delta L. So doing a little bit of algebra, you can show that m over k is equal to d over 2g, or k over m is equal to 2g over d. Now why do we need that? Because when the problem we are given d, the distance it drops, and we are asked to figure out frequency. Well, frequency is simply omega angular frequency divided by 2 pi, and omega is equal to square root of k over m. So since you figure out the k over m in terms of g and d, g you know, you can do the substitution here and substitution there and figure out what f is. You work backwards. In another example, we are told we are given the period for a simple harmonic oscillator. As you know, a period is 1 over frequency, and frequency times 2 pi gives you omega angular frequency. And we're also given the amplitude of oscillation. And we are asked to figure out how long it would take for the object to travel from x equals 0 to x equals 4 centimeters. So we have an object that is going from x equals along the x-axis from 0 position to a 4 centimeter position. Obviously the object is moving to the right, so what we need to do is use the kinematic equation of simple harmonic motion. The one for position is x equals a cosine of omega t plus phi naught. Omega we know because we're given the period, so you can calculate what omega is using the expressions up here. And a we are given, but we do not know what phi naught is, so phi naught we need to figure out. Now to figure out phi naught, let's say that the object is at x equals 0 at time 0 seconds, because after all we are interested in figuring out the time it takes for it to travel to 4 centimeter position, so we can say that at 0 it's at 0 seconds. That's where we start our stopwatch. Now at x equals 0 centimeters, we have the kinematic equation reduces down to a cosine phi, since time is 0. So if you put in time 0 there, omega term disappears. And the solution here is phi naught is plus or minus pi by 2. So, but now you need to choose the appropriate route. Well, we know the object is traveling to the right, and in the previous lecture we said that simple harmonic motion can be described in terms of the projection of an object moving in a circular path, the projection along any diagonal. So here if we take the diagonal, the horizontal diagonal, and we'll call that x, if the object is moving to the right, then we are dealing with the lower half of the circular path. The object starts here, its projection is 0, and the object, when it's over here, the projection is at 4 centimeters. In the upper half of the circle, the motion of the object along the x-axis is to the left. But since here the object is moving to the right, then it's the lower half of the circular path that we care about. Therefore, phi naught is minus pi by 2. Angles from 0 to pi are describe the motion the object moving to the left, and from angles from 0 to minus pi are the describe motion to the right. So it's a negative solution that we want for phi naught. Now that we have figured out what phi naught is, essentially use the kinematic equation and say that okay, it's 4 centimeters, we have our is equal to our amplitude times cosine of omega t plus phi naught, which we said is minus pi by 2. Right? And here we know a because the problem has given us a, and we know omega. T is the only unknown, so you can go and do your little algebra to figure out what t is. Since we started, we said that at x equals 0, time was 0, then t is the amount of time that it would take for the object to move through that displacement. In another example, it's a good example which involves both linear analysis as well as simple harmonic motion analysis. We have two masses, M1 and M2. M1 sitting on top of M2 and is held there by static friction. Now we are told that uh, these masses undergo simple harmonic oscillation with some periodicity T, so we know that we can figure out what omega is through this relationship. So we know our omega. And we're also told that when the amplitude of oscillation reaches A, then mass M1 begins to slip, i.e. when A at amplitude A max, then the mass 1 begins to slip, and we are asked to figure out what the coefficient of static friction is between M1 and M2. Now let's take a look at M1 and the forces acting on it. Well, there's if the objects are moving to the accelerating to the right, then static friction force on M1 is of course to the right. There's M1G downwards and normal force on mass 1 upwards. I hope you have not forgotten your free body analysis. You're going to be needing it come final exam time. Now, doing a Newton's second law analysis for the forces along the y direction, the net force is equal to 0, of course. We have N1 minus M1G along the y, which means that normal force on mass 1 is equal to M1G. Now along the x direction, the only force is Fs, the static friction force, and that must equal mass 1 times A, according to Newton's law. Now for maximum acceleration, that's when the mass starts to slip. We have maximum static friction force. Anything above that, the mass is going to slip, i.e. M1A max is equal to Fs max from this expression here, and we know what Fs max equals to. That equals to normal force times the static friction coefficient. We figured out that N1 is equal to M1G. Go ahead and do that substitution, and you end up with this expression here, which is A max is equal to G mu s. So if only we knew what A max was, but we do know what A max is. A max is the maximum acceleration for the simple harmonic oscillation that we have here. After all, these masses are oscillating back and forth in a simple harmonic manner. Let me bring that back. There. So A max, from our kinematic equations, we know that A max is equal to A max. Well, maximum acceleration is equal to maximum amplitude times omega squared. That's from the previous lecture, if you recall. I had said that the maximum acceleration of the simple harmonic oscillator is equal to maximum amplitude times omega squared. So go ahead and substitute in this term instead of A max, and you end up with this nice little expression, after which you can solve for mu s, which is equal to A max omega squared divided by G. Well, I hope you find these examples useful in doing the assignment for this week, and please work through the practice problems that I gave you, and if you have any questions, either email me or try and come to the supplementary instructional classes to seek some help. I shall see you on Saturday, and good luck to all. Thank you.